Okay, this is the second in a series of 3 Gcse revisions for Unit 2 from the AQA. Hopefully these are helpful. This topic is all about electricity, both static electricity and current electricity. So we start with static electricity. Static means still, so it means charges that are not moving. And to get that, we can do it by friction. So here you've got 2 different methods. What you can do is rub a cloth against the rod, and what may happen is electrons will be transferred from the rod to the cloth, leaving the cloth as a minus charge because it's got more electrons, and the rod is positive. Remembering that it's only electrons that are free to move, and electrons are minus, so they move from one to the other. And other ways, for different materials, the electrons may rub from the cloth to the rod, leaving the rod with a minus charge and the cloth with a positive. You'll see that they've got equal and opposite charges. Things happen in everyday situations. Static electricity is caused by friction, by rubbing. Basic law of electrostatics is quite simple. Opposites attract, so the rods at the top would be pulled, drawn towards each other with an opposite force. And if they were the same charges, both minus, then you'd see them repel, push each other apart. Same would happen with 2 positives. A Van de Graaff generator, I'm sure you've all seen one. This is how it works. The rubber cord rubs around here and causes static electricity by rubbing. And what you see is a buildup of charge. So in this case, we've got a buildup of positive charge here. If it's connected to the earth, then electrons, which are free to move, will move up here and will discharge the Van de Graaff generator. If that is done quite quickly, then you may well see a spark. You may get electric shock that goes through your body. You need to know about uses and dangers of static electricity. So here's one, and then you can apply to the rest. Smoke precipitator. So imagine this is the big cooling towers that you see next to power stations. Power stations produce a lot of smoke, which has dust particles. So when the dust particles of smoke rise up, which is basically just water vapor but with dust, if you've got the charged plates on the side, they will attract the positive charges because we're going to charge up the dust particles with the opposite charge. So as the dust rises up, the positive dust soot will be attracted to the side, be drawn towards it, and the water vapor will go straight through the cooling tower, means that what's coming out the chimney is just pure water vapor, which is not damaging the environment, and then you can clean the soot off the side of the charged plates. So we're using static electricity in action here. Basically the opposites attract and it can put to use. Other uses are photocopiers, where the paper is charged up with the right charge and the ink the opposite charge, so it sticks to the right part of the paper. And same with paint spraying. For example, spraying car bodies. Car bodies are usually made of metal, so if you charge that up with one charge and then the paint particles with an opposite charge, then it will spray onto the car body. Electricity is also dangerous in a few situations. Fuel pipes. Static electricity can cause sparks, and if the spark is caused where there's a potential danger because there's fuel or gas, then you could get an explosion. So it's important that when you refuel in your car or refuel in your aeroplanes, that there is no chance of any static electricity build-up producing a spark which could cause an explosion. And in hospitals also, you don't want static electricity to interfere with the equipment. Going on to current electricity, you need to be familiar with these 12 circuit symbols. So quickly going through them, we've got a cell which you must have to get a current. Adding 2 cells or more together makes a battery of cells. You need to connect them up with leads, and you also then can get a bulb to light. Often you put a switch in the circuit so you can turn it on and off. Now this one here is a resistor, which is going to come on more. So the rectangle represents a resistor. The next 3 components are types of resistor. So this one is a variable resistor with the arrow through there, means you can change the resistance. This one, which is again the resistor symbol but with a line through like that, is a thermistor. Therm meaning heat, so it's a resistor that depends on heat. And the last one is called an LDR resistor with arrows coming in to represent light. So it's a light dependent resistor. More light on it changes the resistance. To measure electricity, the current, we use an ammeter, capital A in the middle, and we can also use the power or the voltage measured with a voltmeter. And a few of the components I'll come on to in a minute is a diode and also a fuse. Be familiar with those circuit symbols. In a traditional circuit, here's a very, very simple circuit, a battery here and a bulb, complete circuit, complete loop so the current can flow. What actually happens in the circuit is electrons, which are negative, come from the negative terminal, and they will flow around the circuit, carrying energy to the bulb, and that energy is then turned into heat and light, which is given off by the bulb. The electrons then go back to the cell, to the battery, and collect more energy, and that produces a circuit, which means the bulb is always lit until the circuit is broken. So although we've got electrons going from minus to positive, by convention we talk about current going from positive to negative. Okay, here's some basic ideas when considering circuits. We can measure the electric current. Current is measured with an ammeter, and current is measured in amps or amperes. Capital A there because it's somebody's name, Ampere, Mr. Ampere, so you must use a capital letter. Same with potential difference, which is also called voltage. You might be familiar with voltage, but you may see the term potential difference on an exam. It is the same as voltage, and it's measured with a voltmeter and measured in volts, and it's named after here Mr. Voltaire, so again, capital letter. The third quantity is that of resistance, which again is named after scientist George Ohm, and the symbol is the omega, the Greek letter there, which is capital Greek letter there, to represent ohms. That's how much resistance or opposition there is to electric current. So let's take a look at some simple circuits. Here's a cell and a bulb. The bulb will light. What would happen if you had two cells? Well, you could represent it here. More light, more energy would come off because you've got more energy given to the bulb. So the idea is here that if you add more batteries or more cells together, you get more force, you get more energy, you get brighter bulbs. What happens if you add more than one bulb then? If you've got two bulbs in series, and a series circuit means it's all in one loop, then the current has got to go through two bulbs. So it's got to share its energy out between the two. It sees what's called more resistance, and that resistance means there's less current. So let's look at that in more detail. If a series circuit like this, if you've got 2 amps flowing through the circuit here, that 2 amps is going to go through that bulb, and back, and you've just got one complete loop. Now, like a lot of laws in science, you can't lose current. There's conservation of current. So it doesn't matter where you measure the current in this circuit, it will always be 2 amps. It doesn't matter where you put that ammeter. So the current is always the same. If you look at the current in a parallel circuit, so parallel circuits look like this, the bulbs here, that bulb and that bulb are parallel to each other, and what happens is the current will be divided up. So here comes the current, it gets to this bit, half will go that way and half will go that way. So the current here divides in two, and so the bulb gets equal amount of current, you can get more current. Let's have a look at 3 bulbs. If you put a value on it here, if there was 6 amps coming down here, that would get 2, that one would get 2, and that one would get 2. And then when all of those currents join up again to go back to the battery, obviously you will get the 6 amps there, and that 6 amps will go back through the cell. Let's have a look at voltage or potential difference now, measured with a voltmeter. Voltmeter is always put in parallel. This is parallel to the battery, so if it tells you it's 6 volt battery, it's telling you the voltage across the battery. If you've got bulbs in series, 3 in series here, and they're identical, you've got 6 volts, I'm sure you've guessed it, that each one would share the voltage, and the voltage would be 2 volts, 2 volts, 2 volts to add up to 6. If the voltmeter went across 2 bulbs, because that's 2 and that's 2, you add together, that voltmeter would read 4 volts. Okay, and if we look at voltage in a parallel circuit, when 2 bulbs are put across each other in parallel, you can see they're both connected directly to the battery. So the rule here is that both those voltmeters would read 4 volts, not dividing it up this time, they both get 4 volts each. So in summary, in a series circuit, the current is the same at any point, but the voltage will be split up over each component in that series circuit. In a parallel circuit, it's the current that splits up, but the voltage stays the same. Worth remembering these two simple rules. Okay, moving on to resistance. Resistance is how much it resists or how much it opposes a current. So the higher the resistance, the more it tries to slow down or stop the current, and it's measured in ohms. So a higher amount of ohms means more resistance and less current. Here's Ohm's law equation. Resistance can be worked out by how much voltage there is per current. Again, coming back to our equations here, nice easy one to remember, VCR, you've heard of VCRs before, will help you rearrange it, making sure you've got the units correct. So here's an example of an exam question. So if this voltmeter is reading 10 volts and the current in the circuit going around this circuit is 2 amps, then the resistance of this bulb would be 10 divided by 2, 10 volts divided by 2 amps, would that bulb there would be a 5 ohm resistor, and in total you'd be 5 plus 5 plus 5, you'd have a resistance of 15 ohms. Okay, a few more components then. We've talked about bulbs, we've talked about resistors, and this one is called a diode. There's an arrow here showing that a diode is a bit like a valve where it only allows current to flow in that direction and it won't allow it going back the opposite direction. If we measured the current and the voltage for each one, then for a resistor, they are proportional. So if you double the voltage, you'll get double the current, which makes sense. For a bulb, it tries to do the same, but as you get more current through it, it gets hotter and hotter and hotter. The atoms vibrate around more, and what actually happens is this causes more resistance. So you don't get the straight line, you get a curve. Doesn't matter which way around the current is, and you get less current than you might expect because of the temperature effect. And a diode, you'll see the line here, when it's in the wrong direction, you get 0 current, and when it's in the right direction, you will get a current going through it. So a diode allows current going one direction and prevents it going in the opposite direction. Two more components was mentioned in the circuit symbols. LDRs, reminder, it stands for light dependent resistor, and a thermistor, therm meaning heat, istor, resistor, meaning a heat dependent resistor. So if we look at the graphs of how resistance varies with the amount of light, for an LDR, if you put more light, if it's brighter, the resistance goes down. So giving it more energy makes it conduct better, means it's less resistance. And it's the same with the thermistor, but it's temperature that it's dependent on. Higher temperatures means you'll get more current, means you get less resistance. It resists less, so you get a higher current. Quickly on to DC and AC. DC stands for direct current. This is what you get from batteries and cells. So the current and the voltage is just one way. AC means alternating, means it changes direction. And for our mains in Britain, the frequency is 50 hertz. So that means you get one complete wave every 50th of a second, meaning in 1 second you have 50 waves. You can see the current here is going in one direction, it's positive, and then this, when it goes below the line, it's going in the opposite direction. And in Britain, it's 230 volts, our mains, which is standard. If you want to analyze and look at AC, you can use an oscilloscope. An oscilloscope screen looks like this, and you have two settings. The first setting tells you what the voltage is, and that's the vertical, how high it goes. The higher it goes, the more voltage it is. And the second setting tells you the time. So if I plot a graph like this showing the AC, what is the voltage and frequency of this supply? So you count the squares up. You've got 1, 2, 3, 4 squares up on a setting of 1, means that you've got 4 squares, 1 volt, so it'll be 4 volts. From there to there is 4 volts, and it goes minus 4 volts that way. And if you look across, you'll see that one complete wave is 1, 2, 3, 4, 5, 10 squares along. So 10 squares for 0.2 volts for every square means you've got 2 seconds for one wave. So if you get one wave in 2 seconds, it means you get half a wave per second. And here's another wave. If you looked at that on the same settings, that would only be 3 volts. And you've got 2 waves now in the same time, so it would be half the time for one wave and therefore double the frequency. So you'd get 2 2 waves in 2 seconds, so it'll be 1 wave per second. Common question, and please remember this, if you ever want to wire a plug, you must remember the colours. The earth wire here is the green and yellow stripes, connect the top. The blue wire is the neutral wire. You have a insulation here, everything must be insulated to stop electric shocks. The live wire is coloured brown, is connected to the fuse, because that carries all the current. And you make sure that you have a good cable grip to stop the cable falling out. You must remember those colours. The neutral wire is where the electricity returns, and the live wire is where the electricity goes into the device. A little bit about fuses here. These is the fuse here, connect the live, as I said in the last slide. Fuses are safety devices. They are there, they're not used unless there's a problem. If there was a problem and a very large current flows, then the fuse would melt, because inside the fuse is a tiny, thin wire. So a 5 amp fuse is thin, meaning that if 5 amps goes through it, it'll get so hot it will melt and it'll break the circuit to protect the appliance. You can work out the fuse by working out the power. Power of device is worked out PVC. PVC, I'm sure you've seen and heard of. You can remember that and rearrange that. If you want to work out the current from power, you can do it like this. Toaster, typical power rate 960 watts. So you divide that by that, it gives you 4 amps. Now if you had a 4 amp device, you would choose the next fuse up. Fuses come in sizes 3, 5 and 13, so you'd go to the next one up, which is 5 amps. Meaning if there was a fault on the toaster and this 4 amp went up to 5, because there's a fault, the fuse would melt and make it safe. So you can go through this table and see that divided by that is equal to that, then you always go the next fuse up. Energy and power. How is energy related to power? Well, power is how much energy there is per second. So 1 watt would be when you have 1 joule for 1 second. In other words, you can put it into this triangle again to work out the relationship between power and energy. So if you had a 100 watt light bulb, it would be transferring 100 joules for every second it was used. It's gone on to earthwise. You will see in all electrical devices, if they have got a metal case, there will be an earth wire connected to it, meaning the case is all connected to earth. The reason we do that is if there was a fault and the appliance touched, the case of the appliance touched the live, if you touch that, you will get electric shock. But because the earth wire is connected, any excess current will go surge to earth, and then the fuse will melt, or commonly blow. So the fuse and the plug will melt, break off the circuit and protect it, mean that you won't actually get a shock. Most modern day appliances are called double insulated, meaning that there are no metal parts on the outside, which mean actually you don't need an earth wire. And finally, for hire only, you may be asked to consider charge. Now, charge is measured in coulombs. Charge is a concept of how many electrons are actually flown in a circuit. You can relate charge and current like this. Charge is current times time. You will be given the equation on the exam, and again it's a case of rearranging it to find out what you want. But remember, charge is measured in something called coulombs, again named after a scientist, so it's a capital C.